In this lecture, we're going to have a look at how to find matrix inverses if they exist. And then we're going to look at the link between matrices, vectors, and systems of linear equations. So we already have seen the definition of a matrix inverse. Here's a slightly different wording, but it's exactly what we've seen before. If we have two square matrices of size n, so this is their square, so they're n by n, such that if we multiply them together in either order, we end up with the n by n identity matrix. So remember, this is the matrix which has ones on the diagonal and zeros everywhere else. Then we say that each of these matrices is invertible and they're the inverse of the other. The way the textbook is just saying is that A is invertible and B is the inverse, but similarly we have that B is invertible and A is the inverse of B. And in this situation, because we're talking about the multiplicative inverse, we would write that B is equal to A to the minus 1. Now it's worth being very careful here. If we have some matrix A, I'm just going to use a 2 by 2, so let's have A12, A21 and A22, then A to the minus 1 is not anything crazy like 1 over A11, 1 over A12, whatever crazy thing you might think. This A to the minus 1 is the inverse of A, and it could look quite different from A. Okay, so how can we go about finding this square matrix? If we have a square matrix, how can we go about finding its inverse if it exists? Because remember, we showed yesterday that not all square matrices have inverses. Well, it's going to be helpful to look at an example. So let's think about what it is that we want to do. Suppose we've got this matrix here, 1, 1, 3, minus 1, and we want to find an inverse. That means that we want to find a matrix with elements, say, x, y, z, w, so that when we multiply these two vectors, these two matrices together, we get the 2 by 2 identity matrix. So if we think about actually doing this multiplication, what do we get? Well, we've got a 2 by 2 matrix multiplied by a 2 by 2 matrix. We can multiply them together and it's going to give us a 2 by 2 matrix as a result. Let's look at what the entries will be. So our first entry will be the first row of the first matrix dot producted with the first column of the second matrix, so that's going to give us an x plus z. Then we've got our second entry in the first row will be first row times second column, so that's going to give us y plus w. And then we're going to have second row times first column, so that's going to give us 3x minus z. And then finally we're going to have second row times second column, which is going to give us 3y minus w. So if we actually multiplied out the left-hand side, that's what we get. And we want this to be equal to the identity matrix. And as we know, when two matrices are equal, we need to have the corresponding entries are equal. So we need to have that x plus z is equal to 1, y plus w is equal to 0, 3x minus z is equal to 0, and finally 3y minus w is equal to 1. So actually this gives us a set of 4 equations that have to be satisfied. So we have 4 equations and we actually have 4 variables, x, y, z and w. So we've got the equation x plus z must be equal to 1. We've got the equation y plus w must be equal to 0. We've got the equation 3x minus z is equal to 0. And finally we've got the equation 3y minus w is equal to 1. And these four equations must be satisfied simultaneously in order to find values of x, y, z, and w so that our original matrix has an inverse. So let's think about how we would go about doing this. Well, if you have a look over here, we really have two equations and two unknowns, and over here we have two different equations and two different unknowns, and we know all about how to solve systems of linear equations. So we could solve this system by Gauss reducing 1, 1, 3, minus 1, 1, 0, and we could solve this system by Gauss reducing 1, 1, 3, minus 1, 0, 1. But notice what's going to happen. Because we've got exactly the same thing on the left-hand side for each of these Gauss reductions, the row operations that we do in both cases will be exactly the same. The only thing that will change slightly will be what happens in our columns on the right-hand side of the augmented matrix, because these are slightly different. So you could do two lots of Gauss reduction, but you'd end up doing exactly the same row operations. So what we're going to do instead is we're going to combine this, and we're going to Gauss reduce a kind of extra augmented matrix. I'm going to Gauss reduce with two columns on the right of this line separating our augmented matrix. So it looks crazy, but it might just work. If you're feeling unhappy with this, then by all means Gauss reduce these two matrices separately, but you'll see that you end up just doing the same thing. Okay, so let's go ahead and Gauss reduce this. So you want to use exactly the same method. So the first thing you want is that your top right hand corner is a 1. It already is, so that's great. So the next thing is that we take all the entries below that and get them to be 0. So we need this 3 to become a 0, and the only way that we can do that is to say row 2 minus 3 times row 1. So we're not doing anything to our first row. It's only our second row that we're changing. Now I've got 3 minus 3, so that's 0. I've got minus 1 minus 3, so that's going to be a minus 4. I've got a 0 minus 3, so that's going to be minus 3. And then I've got another column, which I'm not used to, but that's okay, which is a 1 minus 0, so that's just 1. Okay. So next up, we want this minus 4 to really be a 1. So the quickest way is just going to be to divide through by minus 4. So I'm going to say minus 1 over 4 times row 2. So I haven't done anything to my top row. I leave it just the way it was. Got a 0, 1. I've got 3 over 4. And now I've got minus 1 over 4. Okay, so we're almost done. The final thing that we need to do is convert this into a 0, which we'll do by subtracting row 2 from row 1. So I'm going to say row 1 minus row 2. And that's going to give us, I'm going to write down my second row so that I don't change that. So I've got 1 minus 0, which is 1, 1 minus 1, which is 0, so I've got an identity matrix there. Now I've got a 1 minus 3 quarters, which is 1 quarter, and I've got a 0 minus minus a quarter, which is a quarter. And what I claim, crazy as it may seem, is that this set of numbers over here forms a matrix that is the inverse of the original thing we were looking for. So it's worth taking a moment to think how this could possibly be. Let's take some time to look at that. So let's look at what we've actually found here. If we just Gauss reduced this matrix over here, then this would have told us that we would have ended up with this column here. So we would have Gauss reduced until we got 1, 0, 0, 1, 1 over 4, 3 over 4, which would have told us that if we look here, our variables were x and z, which would have said that x is equal to 1 over 4 and z is equal to 3 over 4. On the other hand, if we'd been working with our second Gauss reduction, we would have found that our solution was 1, 4 minus 1, 4. And this would have told us, looking at the variables in the second set over here, that y was equal to 1 over 4 and w was equal to minus 1 over 4. But if you look at how we originally defined the matrix that we were looking for, all the way up here, that was with x, y, z, and w, and here we've got x is 1 quarter, y is 1 quarter, z is 3 quarters, and w is 1 quarter. So what we've worked out is that x, y, z, w is equal to 1 over 4 and that is exactly the right-hand side that we got when we did our Gauss reduction. So we have now used our Gauss reduction not only to solve systems of linear equations, but to find inverses for matrices. In explaining how this all worked, this probably looks a bit horrific. So let's just summarize what we've got. To find the inverse of an n by n matrix, A, what we want to do is Gauss reduce the augmented matrix given by A on the left-hand side and the n by n identity matrix on the right. So let's just do an example. So if we've got, here's our matrix A that we want to find the inverse for. So we are going to Gauss reduce. We put A on the left, and we want to end up with our identity matrix there. And I've made this particularly straightforward so that we're not going to tear our hair out with Gauss reduction. Okay, so we have a look. We've got our 1 in the top left, so that's great. We need to get this to be a 0, so let's say row 2 minus row 1. So not changing row 1. Not changing row 3. And we're saying row 2 minus row 1, so we've got 1 minus 1, which is 0. 2 minus 0, which is 2, 0 minus 0, which is 0, 0 minus 1, which is minus 1, 1 minus 0, which is 1, and 0 minus 0, which is 0. Okay, well, that's nice. We've got a diagonal matrix, so really if we can just convert this 2 into a 1 by dividing row 2 by 2, and this 3 into a 1 by dividing row 3 by 3, we'll be good to go. So let's finish that up. Not changing row 1 at all. We're going to say half times row 2. It's going to give us minus 1 over 2, half 0. And we're going to say a third times row 3. It's going to give us 0, 0, 1, 0, 0, and a third. And the thing that I claim is that the inverse of A is equal to this bunny that we have here. So let's see, let's check. So we know that if this is true, then we should have that A times its inverse should give us the identity matrix. So if we take our original matrix A, which was 1, 1, 0, 0, 2, 3, 0, 0, 0. Let's just check I got that right. And we're going to times that by this matrix here. Let's see if we get the identity matrix. Well, we've got a 3 by 3 times by a 3 by 3, so we can do the multiplication because our inner dimensions are the same, and we're going to get a 3 by 3, so things are looking possible. And let's work out. So first entry is first row times first column, so that's going to give us a 1 times by 0 times by 0. That looks good. Our second entry will be first row times our second column, and that's going to give us all zeros. Similarly, we'll have all zeros here. Second row first column is going to be second row times the first column, so that's going to be 1 times 1 minus 1 plus 0, so that's also a 0. Phew. Okay. Second row times second column, I'm going to get a 1 times 0 plus 2 times a half plus 0 times 0, so that's a 1. And if you keep filling in, you'll see that we do end up with the identity. So this method of Gauss reducing an extremely augmented matrix is the easiest way to find your identity. To find your inverse for a matrix. So let's look at some properties of matrix inverses. So as you probably know without even thinking, if you find the multiplicative inverse of a number like 6 is 1 over 6, and if you want to find the inverse again, the inverse of the inverse is just going to be 6, because it's going to be 1 over 6. And the same thing works here with inverses. If you can find an inverse of a matrix A, then the inverse of that inverse is just A, which is exactly as we would expect. Now this rule is a little bit different. If you have two matrices, A and B, and you can find their inverses, then it turns out that the inverse that you get when you multiply A and B is the multiplication, the product of the inverse of B times the inverse of A. So there is a change in order here. The inverse of A times B is inverse of B times inverse of A. And you could actually prove that for yourself if you wanted, but it's worthwhile just remembering. So this is important. This is part of the whole matrix multiplication is not commutative. So I want to talk a little bit about matrix equations, because this really pulls together everything that we've learnt about matrices and vectors, and you've probably seen already, now we're including solving equations. So we can write and solve equations involving matrices. For example, if we have the matrix A, which is this 3 by 3 matrix, and two column vectors, and the x vector is x1, x2, x3, and column vector B is minus 3, minus 4, minus 2, then we can write the matrix equation A times X is equal to B. So let's just check. So we've got A is 3 by 3, X is 3 by 1. So we can multiply those together and we should end up with a 3 by 1. So this is a valid matrix equation. So we could ask, what are the values of x1, x2, and x3 that make this equation valid? And one way to think about it would be to think about how we solve equations with scalar variables. So for example, if I gave you the equation 6x is equal to 12, well, you might say, well, I'm just going to divide both sides by 6. But what you're really doing when you solve an equation like this is you're multiplying both sides by the inverse of 6. So what you're really doing is you're saying, I'm taking the inverse of 6, which is 1 over 6, and I'm going to multiply both sides. And as a result, you get 1 times x, which is equal to 12 times 1 over 6, which is 2, so x is equal to 2. So although you think about it as dividing through, if you were to remember way back when you did this for the first time, you're actually multiplying by the inverse. And we can use the same idea here. If we can find an inverse for matrix A, then we could say, well, if I've got A times X is equal to B, then if my inverse from A exists, then I can multiply on the left, so I am being careful of order here, and say A times A minus, so A inverse times A times X must be equal to A inverse times B. But this is going to give me an identity matrix times X, which is going to be equal to A inverse times B. And you can check, but the identity inverse, which will be n by n, or 3 by 3 or whatever, is going to, multiplied by this vector here, will just return that vector, because that's what the identity does. So we could solve this equation like so. So if we can find this inverse, then we just multiply b by it, and that will tell us what x is equal to. So let's go ahead and do that, because it's going to give us a little bit of practice with finding inverses. So here's my matrix A, and I want to find its inverse. So we know how to do this. We put the augmented matrix with the identity on the right, and off we go. So I'm going to leave you to do that and come back and write down the answer when you're done. So if you work through your Gauss reduction, what you should find is you have an identity matrix on the left, and your matrix on the right looks like this. So this tells us that the inverse of our matrix A is minus 4, 4, 3, 1, minus 1, minus 1, minus 3, 2, 1. So if we want to calculate the vector x, then what we need to do is we need to multiply our vector, our matrix inverse with our vector b, which was minus 3, minus 4, 2. So if we do this multiplication, what do we get? Well, we've got a minus 4 times minus 3, so that's a 12. Then we've got a minus 4 times a minus 4, so that's a minus 16. And then we've got a 3 times 2, which is 6. Then our next entry is going to be minus 3 plus 4 minus 2. And then we should have 9 minus 8 plus 2. And finally, if we do all the multiplication here, I think we'll get 2 minus 1 and 3. So this tells us that x1 equal to 2, x2 equal to minus 1, and x3 equal to 3 solves this matrix equation that we had over here. But this might seem vaguely familiar, and in fact we can look at matrix equations in another way, which will make the link to solving systems of linear equations. So let's think about what we could have done. We found the inverse of matrix A, and so multiplied on the left of both parts of this equation to find x. But we could first have multiplied out A times x. So let's have a look and see what that does. So if instead I'd said A times my matrix x what I would get would be, for my first entry, because remember this is 3 by 3 times 3 by 1, so I'm going to end up with a 3 by 1. So I'm going to have 3 entries. My first entry would be x1 plus 2x2 minus x3. My second entry would be 2x1 plus 5x2 minus x3. And my third entry would be minus x1 minus 4x2 plus 0x3. And given that we have the equation over here, this is equal to b, this has to be equal to minus 3 minus 4, 2. And so if we have a look at this, where we have this vector is equal to this vector, this is the equivalent of a system of 3 equations and 3 unknowns, because we know that we have to have that x1 plus 2x2 minus x3 is equal to minus 3, because so for this equation to be true, we need x1, okay, that's a terrible color, let's use that one, x1 plus 2x2 minus x3 must be equal to minus 3. We also need to have that the second row matches, so we need to have 2x1 plus 5x2 minus x3 is equal to minus 4. And then finally we need to have that minus x1 minus 4x2 is equal to 2. So what we've actually done is, as our alternative view, we've taken this matrix equation and we've written it as a system of 3 equations and 3 unknowns. And we know how to solve those. We Gauss reduce using the coefficients on the left and the augmented matrix with those coefficients on the right. So pulling these two together, we find that there's really a huge link between matrices and systems of equations. So what we have is that if we have any system of linear equations, so here we've got m equations and n unknowns or variables, we can rewrite this as a matrix equation where our matrix A takes all the coefficients of the variables across the equations. Our x is our variable vector, each of which each component is one of the n unknowns, and our b is our right-hand side answer solution. So, what does this mean? Well, it means that we've really just found another way of solving systems of equations. So the one option, if we're using this form over here, is to Gauss reduce in the way that we first solved the equation, back before we learned about matrices. But the second way that we could solve is to find A inverse, if it exists, and then work out the equation our variable x is equal to A inverse times vector b. So they both involve Gauss reduction, remember, because finding the inverse of a matrix involves Gauss reduction. So the one thing that I haven't mentioned is we've said that not all matrices have inverses. And how do you know if the matrix doesn't have an inverse? Well, it's just going to be that the Gauss reduction doesn't work. You're going to get a row of zeros before the line and then something else after the line, so it has a no solution. So just to clarify the rules about matrix equations and how they relate to working with real algebra, so here we're thinking about reals as in reals, not something that definitely exists as opposed to doesn't. So the way we solve in real algebra, if you're trying to solve for x, is you multiply on the left by the inverse of the coefficient of x. And what you're really using in the next step is the associative property of real numbers, which gives you an A inverse times A, which gives you 1, and that's how you solve it. And in fact, we're doing pretty much exactly the same in matrix algebra. So we've got A times some variable that we're trying to solve for is equal to some series of constants. Multiply on the left by the inverse if it exists. Then you use the associative property of matrix multiplication to get the identity matrix, which acts like one acts in real algebra, and there we've got a solution. The only thing to note here is that this does not always have a solution in the matrix form. So even if you have square matrices and everything has the right coordinates, the right dimensions, you might not always be able to find a solution. Whereas in this case over here, so long as your B, so long as your A is not equal to 0, you can always find a solution. So I just want to finish off by noting a couple of the little oddities about matrices. So one of the things that we've already seen is that matrix multiplication is not commutative. So multiplying A times B might be different from B times A. Doesn't have to be, but it might well be. And here are some things for you to try and find examples of. So there exist matrices A and B, which when you multiply them together give you 0, but neither of them is the 0 matrix. So this is a bit weird because we know that if you have real numbers, then if we have x times y equal to 0, means that either x is equal to 0 or y is equal to 0. But strangely here, with matrices, that's not the case. You can have two matrices which you multiply together give you the 0 matrix, but neither of them is a 0 matrix. So see if you can find yourself an example. And in fact, it gets worse than that. So we can have a matrix A, which isn't the 0 matrix, and yet when you square it, it gives you the 0 matrix. Now we know that if you have x squared and x is a real number, then we must have that x is equal to 0. So matrices really behave quite differently. So here's something else that's odd. We've got matrices where if you square the matrix A, it's equal to itself, but it's not equal to the identity matrix, and it's not equal to the 0 matrix. So again, if you think about if we had real numbers where this was the case, so if we had x squared is equal to x in a real number, well then we'd want to solve this equation. We'd say, well, x squared minus x is equal to 0, so we can take out a common x. So either x is equal to 0 or x is equal to 1. Those are the only two options. But I challenge you to find some examples of matrices A where you have that the square of the matrix is equal to the original matrix, but it's not equal to the identity or the 0 matrix. And here's another curiosity. So we can also find a matrix whose square is the identity, but who isn't equal to the identity or minus the identity. So that's the equivalent to thinking of having some real number which is equal to 1. If we want to solve that, you'd say x squared minus 1 equals 0, which we factorize. So x is equal to 1 or x is equal to minus 1. So these are things in which the matrices act quite differently from real numbers. So as a challenge, see if you can find some matrices that behave like this. So that brings us to the end of this section on matrices. Spend some time getting familiar with it. Make sure that you're happy with the things where matrices behave like you would expect, and also how they behave that is different to how you might expect.